Hi, welcome to Mathematics with Tom. I am Tom, and in this video, what we're going to do is we're going to learn how to find eigenvalues and eigenvectors of a matrix. And remember what we just learned. We learned, I'm going to bring your attention to this area over here. This is what we learned. We learned that an eigenvector, when you multiply it by a matrix, gives you the same vector times some scalar. So in the vector, whatever it is, x, when you multiply it by the matrix A, the vector x remains in place, but the result ax might be scaled somewhere. So let's take a look at this. Here we go. This is let's go back to our white, it's nice and clear. This is 6.1 in our textbook by Gilbert Strang. Today we're going to find the general solution. The general solution for eigenvalues. All right, here we go. So how does this work? Well, let's take a look at this. So what we said is an eigenvalue is a times x equals lambda x. And lambda is a scalar. Lambda is a scalar. And for simplicity, we'll just do it this way. Assume A is 2 by 2. 2 by 2. All right, here we go. Let's solve this. Now, we've learned how to solve the problem ax equals b, but this is ax equals a scalar times x. Well, we haven't done that, so let's think about this. Let's do this. Let's go ax minus lambda x equals 0. That seems like a reasonable thing to do. Now, I'd really like to factor that x, but I can't. Because if I factor the x as it is right now, then what I would be doing is I would have a vector times a scalar. Well, that doesn't make sense. So what I need to do is I need to somehow create this so that I can factor. Well, the key to doing that is let's write this as ax minus lambda times the identity matrix times x equals 0. Okay. Now, lambda times I is a matrix, and A is a matrix. So if I factor out the A, I have A minus lambda times I times x equals 0. Now, here's where we have to do a little bit of thinking. The step is simple once you see it, though. But the logic or the thought process is fairly involved. Notice this. Notice x equals 0 is a solution. But it's not interesting at all because a times the 0 vector is very simply just the 0 vector again. Nothing happens. So, but we're interested in vectors where things do happen. In other words, we want x's that are not 0. Oh, that changes the story dramatically. Why? Why? Because when x is not 0, we're solving a null equation, then the matrix of A minus lambda I, this whole thing is a matrix. I should put then, let me write it that way, then the matrix of A minus lambda I must be singular. Must be singular to have non-zero solutions. Singular. To have non-zero solutions. Okay, well, why is that important? Well, what is important about this is that when we have a when we have a singular matrix, what we do know is we know its determinant is 0. So in other words, then I can say that the determinant of, if I take the determinant of both sides, so you could apply the determinant. Oh, no, I'm sorry. Must be singular to have non-zero solutions. So the determinant, there we go, the determinant of a minus lambda I must be 0. Okay. So that's the question. What we need to do is we need to solve the determinant of a minus lambda I to find eigenvalues. All right, so here we go. Let's actually try this. So what we have is we're going to take the determinant of the matrix. Oh, let's write it this way. We're going to take the determinant of, so the matrix A is just a 2 by 2, A, B, C, D, minus lambda times the identity, that's lambda 0, 0, lambda. Okay, and this has to equal 0. Well, this becomes the determinant of A minus lambda B, C, D minus lambda equals 0. Now let's take the determinant. I know that might look a little rough, but it actually becomes quite interesting. So if I take the determinant of this, I'm going to get, remember I multiply down the diagonal, so I'm going to have an A minus a lambda times D minus lambda, and then I go minus, then the product of the anti-diagonal, well, that's minus BC, that has to equal 0. So let's distribute this. So I'm going to get a lambda squared. Then let's see, what else do I get? I get a minus lambda A minus, oops, I'm going to write it the other way. It'll look a little bit more natural that way. Minus A lambda minus D lambda. And then I'm going to get a plus, I have an AD minus BC equals 0. Okay, let's factor the lambda from those second and third terms. This is a lambda squared minus, notice this becomes A plus D times lambda plus, I'm going to put parentheses, A times D minus B times C equals 0. Okay, and I think we have just enough space here. Actually, let's go to the next page. I'm going to go to my next page here. And what we have is this. So I'm going to just bring our key points. Is that we have the matrix of A is A, B, C, D. And we have just arrived at lambda squared minus A plus D times lambda plus A times D minus B times C equals 0. This equals 0. Well, first off, look at this. A plus D, that's the sum of the diagonal elements. We call this the trace, the trace or the trace of the matrix A. And notice, what is this? This piece right here, that's familiar. That's just the determinant of A. And there we have it. So we can solve lambda squared minus the trace of A times lambda plus the determinant of A equals 0. If we solve that, then we have now found all of our eigenvalues. And let's try an example to see how this works. Well, first off, before we do that, let's just remember you hope the ideal solution is that you can solve this by factoring, but oftentimes you can't. So how would you solve this? Well, this is a second order differential. Sorry, this is a second order equation, and you solve it with the quadratic formula. So lambda is equal to minus the b term. Well, that's minus the trace of a, so that just becomes the trace of a plus or minus the square root, this would be a big one, the square root of b squared, so that's going to be the trace of a squared, minus 4 times the a, which is just the 1 on the lambda squared, times c. Well, the c is the determinant of a. So the square root of all of that, that was a crooked square root line, there we go, divide that by 2. And there you go. Now you've just found your 2 eigenvalues. And so that will give you, this will give you a lambda 1 and a lambda 2. Okay, so that is the general solution. And now what I'd like to do is let's see if we can solve that. So our example in the first video to introduce this was a is 2 minus 1, 2. And you know what we're going to do is we are going to go through this process. Now, there's 2 ways to do this. One is you can just learn and memorize the formulas, and that's fine. However, I think if you're stuck, if you're ever just like stuck, where do I go? I can't remember the formula. Just remember to solve. Just start out by solve the determinant of a minus lambda I equals 0. That's the whole basis of the problem. So in other words, if I do this, then I have the determinant. Let's go up here. We have the determinant of 2 minus 1, 2. Minus, and you won't have to do this step every time. I'm just doing it just to show you how it all comes together. Lambda 0, 0, lambda. This is going to equal 0. So this becomes the determinant of 2 minus lambda minus 1, 2 minus lambda equals 0. And now we take the determinant, so I get a 2 minus lambda times a 2 minus lambda minus, I have a negative 1 times a negative 1 equals 0. Let's clean all this up. I'm going to get a lambda squared minus 4 lambdas plus 4, and then I have a plus 1, I have a minus 1 equals 0. So really the problem is lambda squared minus 4 lambda plus 3 equals 0. Now this factors. So you know what? If it factors, let's run with that. So this becomes a lambda plus 3. Oops, no it doesn't. It becomes lambda minus 3, lambda minus 1 equals 0. So here we have it. We have lambda is 1 and 3. Okay. Now, these are eigenvalues. These are eigenvalues. So the natural question then becomes, well, how do you find eigenvectors? So we're going to go to the next page and we'll show you how you do that. So now, so these are our eigenvalues. So let's find, now we're going to find the eigenvectors. Okay, how do we do that? Find the eigenvectors. So here's what we were solving. Remember, the original problem was ax equals lambda x. And then we've been working with we've moved the terms over, and we got a minus lambda I times x equals 0. Well, now we know lambda, so let's put that in. Our problem then Remember, then we wrote the matrix here became a 2 minus lambda minus 1 minus 1, 2 minus lambda. That was our matrix that we were working with. Well, what is this? This is just find the null solution. The null solution. Find the null solution. Well, let's do that. Our first eigenvalue we said is, we'll call it lambda 1, is 1. So here's what you do. You substitute your 1 back into this equation and solve. So now we're going to take this. We have 2 minus 1 minus 1 minus 1, 2 minus 1. And I'm just going to write the augmented matrix with the 0 column. So this is just the matrix of 1 minus 1 minus 1, 1. Now, if you look at this, you can see that each row or each column is just a multiple of minus 1 different. You should always, and at this point, this should always be, this matrix right here must be singular. If it's not, you made some kind of an error. Must be singular. Okay, so if it's not, you made a mistake. Let's row reduce this. Let's row reduce this, and we're going to come up with 1 minus 1, 0, 0. Well, the null solution to this just is that this says here, this first line says that x1 is equal to x2, and we have a pivot in the first column, so this is that x2 is free, or in other words, x2. So our eigenvector x, well, let's write our null solution then is x2 times 1, 1. Whoa, and that's what we found. That was one of our eigenvectors. And now notice this. Because x2 is just a scalar, we tend to write the most simple version of the eigenvector. In this case, 1, 1 is pretty simple. But if you came up with a fraction, then you would just pick some scalar to multiply it so that you just have a nice, simple whole numbers to work with. Okay, but we would say that 1, 1, so x1, our eigenvector that goes with the eigenvalue of 1, is 1, 1. All right, let's do that one more time. So we have that lambda 2, that's our second eigenvalue, so that was 3. So now we're going to just go substitute that 3 right back into this equation this time. So now I have a 2 minus 3 minus 1 minus 1, 2 minus 3. And this is going to be minus 1 minus 1 minus 1 minus 1. Oh, and you can see right away that's going to row reduce. This is just going to reduce to the matrix of 1, 1, 0, 0. And so now this just gives me the equation that x1 is minus x2. x2 is free. And so our null solution is going to be x2 times minus 1, 1. So what we're going to say is x2, our eigenvector that goes with the eigenvalue of 3 is minus 1, 1. And there we have it. That's how we find our eigenvalues and our eigenvectors. And that's how you find eigenvalues and eigenvectors. I hope that helps. Thanks for watching.